Hi, thanks for coming. And I'm Erick from Exit Games. I'm going to share with you here a few insights on what are the challenges when you want to use determinism for building multiplayer games. A little bit of context here. So we're talking about online player experiences, and from the player perspective, which is what matters, they don't care about how you do it. So they just want to perceive that they are in a virtual world that's populated by many players, and that's it. They want to have that with as little lag as possible, so they don't want interfering with the good experience. So on the other end of the spectrum, we as developers, we have a challenge, which is essentially this. There is a game state, which represents what the game is, and we have to keep it synchronized across all game clients, ideally, again, without lag. That's it. But that's the hard challenge that we have to solve. But because this has been done for the past 30 or 40 years or so, there are some common strategies that are really well established and the best ways to do this in different genres or different games. And these, you can divide them into main ways. So one idea that you can come up with is essentially, okay, let's have somebody have the game state and transfer data about the game state itself, like positions, rotations of all the objects in the game from this server, etc., across all game clients. So this is the essence of known strategies for example, first-person shooters. And there are two main ways of doing this. One is called, it's known as Snapshot Interpolation. Another one is called representation state transfer. I'm going to give you guys a little bit details on each one of those. There is a completely different way of doing state synchronization, which is essentially not sending across the network data about positions, rotations of the objects themselves, but actually sharing whatever the players are pressing as input. And this can be done in two ways. The Lockstep mode, which is very well known for RTS games, and there's also the predict rollback mode, which is the subject of our talk in general. So one by one here, what is the whole thing about snapshot interpolation? In essence, you have a server, and as a player, you send comments to the server. You might have local prediction or not. This is nowadays is pretty much mandatory. But in essence, the server has to send the full game state to all clients every tick. You might think this is kind of like naive. It is, but it works in certain scenarios. For example, games like CSGO still use this approach. And it's nice because it's simple to implement, but then you have to work a lot of stuff like have lag compensated raycasts, and it still uses a lot of bandwidth because essentially you're transferring the whole game state every frame across the network. And this is also both uses a lot of bandwidth, but also limits the number of objects you can have in the game. So in essence, you're limited to what the thing you can transfer. There is a more complex way to do this, which is state transfer. So in essence, you still have the same thing about the simulation running on the server and still transferring the data, but now you only transfer partial stuff. You only transfer to my client what I should see. And okay, this might sound ideal, but this is actually a lot more complex to implement. There's a pretty famous talk about the Overwatch team showing, they have a 1 hour talk explaining just how, half an hour of this talk is just explaining how one weapon was implemented using this because of the sheer complexity of this approach, but it's still pretty good. It also has another issue, which is it uses a lot of bandwidth. The reason for doing only partial transfers is not much because of it's better, it's just because it's the only way to do if you want to have a complex game world and still use state transfer, which is transferring the data about the game itself. So if you go the other route, which is transferring input, the old way of doing this is known as Lockstep, and this is common on RTS games, although it was also used on even first-person shooters, like the first Doom, which is let's say the whole start of esports grade stuff, I'd say, in 94, 93? That was using Lockstep. But it's good because the only thing you're transferring is input, so you have a really, really low bandwidth. You can scale pretty much the number of units you have moving. It's pretty much limitless. It's limited by the CPU and not by the bandwidth anymore. And you have a lot of interesting features out of the box, like replays are very easy to implement and so on and so on. The tricky part is that you have to program things in a deterministic way. And the really ugly things is in pure Lockstep, you end up with the problem that you have to deal with input delay, because that's the way to do. You have to program in a way that the game accepts that you do something here, but it will be applied in the game state later, because you have to wait for the input to come from the other clients, and this might be 200 milliseconds, might be half a second on a mobile network. So it's very limited in the applications. It's more like for RTS games, but this is still used today. StarCraft 2 still uses this. You have a lot of mobile games in Lockstep using this because it works. It scales really well as well. But fortunately, there is another way of using the benefits of input-based determinism that does not have the limitations of Lockstep. And this is known as the deterministic predict rollback mode. This is what fighting games use, this is what brawlers use, and this is what can be used in a lot of mobile games and all those things. It's essentially you can come up with a determinism idea for action games. The way this works is you still only share inputs from the clients, but what you do is on your machine here, think about it, as soon as you have input from you simulate that tick right away without waiting anything. And what do you do for the other players? The framework predicts what's going to be their inputs based on the past. And then eventually in 3 or 4 seconds, for example, the input confirmations come from the other clients, maybe based through a server or not, but you receive the input confirmations. What the framework does is compares with the prediction. And if the prediction was right, there's nothing to do. The game state is already in sync because it's deterministic. If the prediction was incorrect, what the framework has to do is roll back the entire game state to the past and resimulate all the frames again, now with the correct input. And this, surprisingly, is the best possible player experience for twitchy games where you have a lot of interference between players. For example, fighting games, brawlers, anything that you need accurate physics, it's done much better if you take this approach. And you still have the ideal things of low bandwidth and all. The very, very complex part here is to achieve the right level of performance, knowing that you have to roll back the entire game state and resimulate the entire game several times when input prediction misses every now and then. So this is what we've been working on for the past 3 years in a product that's well known, but I'm here actually to share some of the insights we came up with while building this. This is just stuff that you can use your own or just talk to us at any moment. We're happy to just talk about it in any way. So first, do you really need this? Why do you need rollbacks for? So first thing is this is the best player experience possible in terms of speed if your game is action-based, it's twitchy, and so it's not. I think that it's not so well known because of the prevalence of the first-person shooter model, and people think that maybe I'll just have a server running the simulation just like I do in PUBG, but that's not the best way to implement all games. The same way that this is not the best way to implement all games, but there are a lot of genres that this is the best way. But then the other advantages is you have low bandwidth, but more importantly, especially for teams, so the guys were talking about, okay, we're 4 guys doing the whole backend here in the previous talk. So is that essentially online multiplayer is no different than local game. Actually, you share the same code that you run for the local split screen version of the game is exactly the same code that runs when you're running the online game. So for the development team, this is really the ideal. So what are the challenges then? The reality is that this is slightly hard to accomplish. First, because engines are not deterministic. So none of the engines out there, out of the box, are deterministic at all. Not only that, even if they were made to be deterministic, they would not support rollbacks out of the box. You need not only to be deterministic, but also to support very, very fast rollbacks. And no physics engine is built with that in mind. Some of them are built to maybe be deterministic, but they're not built for rollbacks. So it also kind of like requires you a different mindset in how to think about the game, although this is the easy part because it actually simplifies a lot of stuff. But in our experience, it seems, I mentioned this before, it seems like because a lot of people is thinking about FPS games a lot, they always think that that's the only solution for solving multiplayer. It's one of the possible ones. So I'm going to talk about two challenges that we were facing that we're happy to give you a few tips about it. So first one is, how do you achieve cross-platform determinism? In summary, you need to write a game engine. So we had to write from the math code to animation tools, navigation, physics, both 2D and 3D. As I mentioned before, there is no physics engine out there that can do rollbacks out of the box. And about fixed point math, so this was what we chose to use, and talking to other people seems to be the best solution anyway. It's like using 64-bit integer to store a number and use 48 bits for integer part and 16 bits for decimal part. You might think, oh, there's another way using like 32 bits that's more accurate, etc. But it has a very, very important drawback, which is the multiplication operation between two fixed point numbers when using Q3232 is 4 times slower than you can achieve with this, because you can do without overflow checks. So don't even think about it. Go for 4816 if you're doing this. I found one of the games here that's using determinism, etc. The guys did the right choice, so they came to the same conclusion. So it's interesting. So if you think about it really a lot and you do it for 2 years, you come up with this conclusion. It's the best possible for fixed point. And this becomes cross-platform deterministic out of the box as a math engine can do. So of course we do everything, we inline everything in C#. We don't rely on .NET compiler to inline it, because on Unity it would not work. Maybe it will work in the future, but we inline it manually, everything. We use lookup tables for the things that would not be so fast to do directly doing in code, with variable density when needed, so we don't explode the memory use. The other challenge is how then to do fast rollbacks. So what you need to do rollbacks, you either need like 2 instances of the game state, one verified with the data that's already like confirmed input, and one that's running, let's say, the tip of the simulation based on the clock, or a ring buffer of game states that you keep moving forward. We use internally the ring buffer solution, but it's fine if you use like the 2 instances only. It's slightly simple, but for the predict rollback itself, it works. In essence, what you need is you need to have a way to copy the complete game state from one instance of this structure that represents a game state to another, and you have to do that very fast. In essence, you need a deep copy. So if you have an object-oriented game state with a lot of classes and instances of them all across memory, you're screwed, because you have to implement a deep copy, because something like this would not work. I mean, if you have object A and you have a copy of object B, but it references object B, this is fast to do, but you keep a shared copy of B, and this is a problem, because if you modify B, you have the modification on both copies, and this is not what you need. So you need to create a deep copy mechanism, and in object orientation, this is going to be heavy. I have a few numbers to share with you guys on the experiments we did with different kinds of data structures and different kinds of implementations of this on C#. So the number itself is on a specific machine, but for comparison's sake, it's all on the same machine, same size, and same thing. So if you have a very, very basic game state structure, kind of like that, and you have 100,000 instances of that thing, is just an example. The most naive way of copying this would be serialize and then deserialize in another copy, and that's, of course, not a usable thing, but for comparison, that would take 3 seconds to do. Then if you implement a manual deep copy, oh, you're much better. You can do that in 100 milliseconds. And if you're talking about 1K instances, we're talking about 1 millisecond, we might be good, really, because 100,000 units might be too much. But notice that this is a very, very simple and shallow game state. There's not much data in here. And the thing is that if you think about structs in C#, for example, and not objects, which are blittable, they live in the stack, or they can be put in a buffer or in an array, just using array copy puts you down from 100 milliseconds to copy the whole thing to 3 to 5 milliseconds right away. So just moving from classes to structs in C#. Then you can understand which was the option we went for. If you go one step further, instead of using a normal C# array, you just have a buffer in memory and you do a mem copy on top of the same amount of data, it's like even 3 to 5 times faster. So that 1,000 instances is going to be 1/100th of 1 millisecond to do the rollback. So that's what we choose to go to. So if you can, do that. If you're going with array of blittable structs, could be okay as well. But don't try anything else. So a few tips to end here. So we came up with this thing that the game state that our framework helps you create ends up being like this memory-aligned blittable structs using a lot of old-fashioned pointers and so on and so on. We never allocate anything on the heap, so no garbage collector being called because of the simulation. So depending on the game, this might fit into the L2 cache of the processor. This is so nice because you also get a lot of performance benefits from getting cache hits while you're doing the game loop. It's surprising. It's just something that comes out of the box because your game state is on a buffer and it fits into the L2 cache. And this is really, really common. And even in mobile games, some of our customers are able to do this because of these ideas. Always inline everything, even your code. So you start without it, then you later inline it. You can get 10x performance improvement just by inlining stuff. We do a lot of multi-threading internally. For now, we're not exposing this to the customers, so it's more like the engineers do that, and it comes out of the box, for example, on our physics engine and so on. So if you're thinking about doing something yourself, it's nice to first have it working well for you as a team. Later, you expose to whoever else is using your stuff, even inside the team. About API, one idea that we came up with that is working well is don't expose anything networking-wise. So the game developers write the game as if it was a local game. That's something that's by design. We don't even expose rollbacks on the API. From the code, you don't know a rollback is happening, although game design-wise, you are aware of it and you plan some of the visual corrections and interpolations you apply are going to be aware of the amount of rollbacks you're going to have. But in the code itself, you don't have to worry about it, like do a different code when a rollback is happening or not, because that would just actually break determinism. We use a lot of code generation. This has been the subject of several talks I've been to in different contexts. It's always nice if you can use code generation. It helps a lot. It helped us a lot as well in several stuff. And also write good samples. Even as an internal team, if you write a tool, write a sample of how to use that tool. It's going to help the other developers to catch up and use it correctly with the right patterns. And that's it. I think we still have 1.5 minutes. Thank you for listening.
So we are close in time, but I don't believe the next speaker's around quite yet. So we have time for a couple questions up here.
Is there any reason that you choose no heap allocation against the custom allocators, which would help you to allocate memory for complex structures, and it will be easier for developers not to use continuous memory no heap allocated space?
There is. We try to be pragmatic. So we started with a buffer, a pre-allocated buffer. It's working really, really, really well for all the customers we have. But we are already working on the custom allocator idea anyway, because it also works. It's also a nice idea. And of course, it makes sense to move forward to that. That's a very good question. I think it depends a lot on the speed of the game. this game in the middle here, it's a very fast-paced shooter, and it's available on Steam as a tech demo. It's called Blueless. You can download and try yourself, and then you see how much rubber banding you see, and you can compare two screens. You see the ping and all. But what I know is that most of the time you're not going to see any rubber banding, and what they did is that there's some. We have a lot of control on how much interpolation you want to do for the visuals. What they do is they do an adaptive change on the interpolation factors. So when they notice that the character jumped, they use a little bit more interpolation so it catches up fast. But most of the time they don't use a lot of interpolation, so in essence you don't see a lot of rubber banding when they move direction. It's just a matter of it's more a matter of you fine tweaking the dynamic interpolation you use on the visuals to reduce rubber banding. It only exists in very fast-paced games. So fighting games, for example, they normally don't add any interpolation. They just correct. The players are fine with it. Yeah. What we try to do as a framework is we expose it so you can choose what to do.